Welcome back. In today's explainer, we're taking some pretty complex technical material and making it crystal clear. We are unpacking the absolute fundamentals of magnetic particle inspection, or MPI. So, whether you're an aspiring technician or just someone who's genuinely fascinated by how things actually work, we're going to dive straight into how this incredibly important non-destructive testing method functions out in the real world.
But before we get deep into the physics of it all, let's just stop and ask a really crucial question. Think about a 10-ton steel suspension bridge, or maybe a commercial airplane, or even a high-pressure oil pipeline. How exactly do heavy industries ensure these critical structures don't catastrophically fail without, actually destroying the materials to test them? I mean, we obviously can't just cut a bridge in half to see if it's strong enough. We need a reliable way to look right into the surface of these metals.
So, here's our roadmap for today. We're going to cover what MPI actually is, the physics behind flaw detection, where MPI is used, the 6 key steps of the inspection process, and finally, why demagnetization really matters. Okay, let's jump straight into Section 1. What is magnetic particle inspection? Let's cover the basics.
At its core, MPI lets us pinpoint dangerous flaws in materials completely safely, just by utilizing simple iron filings and magnetic fields. It's actually considered one of the absolute most common non-destructive testing methods out there, mostly because it's incredibly fast and pretty easy to apply. Basically, if a material is ferromagnetic, which just means it can be magnetized, we can use small magnetic particles, either as a dry powder or suspended in a liquid bath, to highlight defects sitting right at or just barely below the surface.
Just take a look at this. Notice how vividly these real-life photos of welded structural steel show those otherwise completely invisible defects popping right out at you. You can literally see how the magnetic particles have just pooled together right along the cracks in that weld. To the naked human eye, these critical structural failures would be practically invisible. But with MPI, boom, they stand out in extreme high contrast, telling an inspector instantly whether a weld needs a repair or if it's a total reject.
All right, moving on to Section 2, the physics of flaw detection, how it actually works.
This all goes right back to high school science class and the basic Earth-like polarity of magnets. Simply put, a magnet is any material that has polarity. Just like our planet has a north and south pole, so do magnets. And the absolute golden rule here, opposite poles pull toward each other, they attract, while like poles repel. That simple, fundamental law of attraction is literally the engine driving this entire inspection process. And right here is the real aha moment. When a part is magnetized, magnetic lines of force flow right through it. But a crack acts like a massive roadblock. Because the magnetic field can't easily jump through the empty space of the crack, it's forced upward, right out into the air, creating what's called a leakage field. And this leakage field suddenly starts acting like a tiny, brand new magnet with its very own north and south poles. So when we apply those finely divided iron particles to the surface, they are intensely attracted to that specific leakage field. They collect right there, totally exposing the hidden threat.
But, of course, there's a catch. Defects like to hide in all sorts of weird orientations. For the best possible sensitivity, those magnetic lines of force need to cross the flaw at a right angle, or as close to 90 degrees as you can get. If the magnetic lines run parallel to the defect, you get almost zero magnetic leakage, and you could easily walk away missing a critical flaw. To combat this, technicians use different types of magnetic fields. Circular fields are created by shooting electrical current straight through the part, while longitudinal fields are produced indirectly, like by putting the part inside a current-carrying coil. Sometimes they even fire off multi-directional magnetization in rapid succession just to make absolutely sure they catch a flaw, no matter which way it's hiding.
Which brings us to Section 3. Where is MPI used? Let's look at real-world applications. Honestly, MPI is everywhere. It secures everything from aerospace components and automotive gears to massive oil pipelines and power plants. It's used on castings, forgings, welded joints, you name it. But here is the craziest part. This highly sophisticated method was basically discovered completely by accident. Back in the early 1900s, this guy named William Hoke noticed something strange. While he was grinding down hard steel parts on a magnetic chuck, he saw the metallic dust forming these really distinct patterns on the metal. Turns out, those patterns perfectly traced surface cracks. He realized the flaws were distorting the magnetic fields and trapping the dust. The idea spread like wildfire, and by the 1930s, the railway industry was using it as their go-to testing method. Okay, Section 4. The 6 steps of inspection. The procedure. Today, this follows 6 highly structured steps. First up is part preparation, getting the surface totally ready. Second is picking your magnetization method, so deciding between those circular or longitudinal fields we just talked about. Third is the application of particle media, choosing wet baths or dry powders, maybe visible or even fluorescent particles. Step 4 is the actual inspection and interpretation of whatever you find. Then comes step 5, demagnetization, which is huge, and we'll dig into that in just a second. And finally, step 6, post-cleaning, to make sure the part is perfectly wiped down and ready for active service.
That perfectly sets up Section 5, why demagnetization really matters as a crucial final step.
Because we're dealing with ferromagnetic materials here, they actually hold on to a magnetic field long after you turn the testing equipment off. If a tech forgets to demagnetize a part, you've got a massive problem on your hands. Just imagine an aircraft navigating with a compass that's being thrown off by leftover magnetic fields. Or think about a freshly installed gear inside an engine. If it's left magnetized, it is literally going to attract dangerous metal shavings right into its moving teeth, totally destroying the machine from the inside out.
So to ensure a part is genuinely safe, technicians use field indicators, kind of like the ones you're seeing right here. They place these gauges against the metal to verify that the dangerous residual field is completely gone. They usually achieve this by passing the part through a demagnetizing coil while running the current down through descending step-down amperage shots.
And listen, this isn't just a friendly recommendation. Safety codes strictly mandate that after that step-down process, the remaining magnetic field cannot exceed plus or minus 3 gauss. If a tech texts the part and that dial reads higher than the threshold, no exceptions. They have to repeat the entire demagnetization process until that strict standard is perfectly met.
Honestly, it's pretty incredible to think that simple, high school principles of magnetism and a bit of iron dust are literally what stand between us and catastrophic structural failures. I really hope this explainer has shifted how you look at the world, kind of revealing those invisible safety nets that heavy industries rely on every single day. So, what do you think? Next time you drive over a massive suspension bridge or buckle your seatbelt on a commercial flight, are you going to think about the brilliant physics of magnetic particle inspection working silently behind the scenes? Thanks for learning with us today, and we'll see you in the next one.